Chapter 6, Population Biology. Population biologists are concerned with factors that affect numbers over time. Prior to discussing factors that affect growth, we need to cover some basic terms and concepts related to population growth. As we discussed in a prior chapter, a population is all of the members of a species living in an area at the same time. From this definition, it should be obvious that it is important to know if any changes occur in the population number. The rate of any change is the number of individuals added or subtracted to the total over a given time. Please note that growth can be positive or negative in this context. If all things are equal and there are no limitations to growth, the population will grow at an exponential rate where the population increases by some fixed rate. We often speak of the doubling time for a population. The outcome of this type of growth is a J-shaped curve. This is an example of geometric rate of increase. If cockroaches reproduce 10 offspring for each adult roach per 3-month period of time, the geometric rate of increase can be calculated as follows. Conclusion: one pair of roaches can produce a population of 20,000 roaches in 1 year. A line graph of population growth of cockroaches. While we talk about growth in the context of unlimited resources, this is never really true. At some point, a resource will become limiting and the rate of growth will decrease. When this happens, the curve will increase, but at a slower rate. This kind of curve is characterized as an S-shaped curve. The top of the S curve occurs near a line called the carrying capacity. Carrying capacity is how many individuals in the population the environment can support given some level of resource, the limiting resource. An illustration of the slowing rate of growth with an S curve. Several factors affect the rate of population growth. They are usually categorized as either density dependent or density independent. Density dependent factors are factors that cause a change in the rate of growth as the density of the population changes. For example, as the number of fish in a lake increase, the amount of food per fish decreases, causing a reduction in reproductive potential. Density-independent factors are those that affect the rate of population growth regardless of the density of the population. An example of this would be a drought that dries up a lake, killing all the fish. The drought was not caused by the density of the fish. How species respond to dependent versus independent factors. This can be influenced by fecundity, how many offspring that can be produced, length of parental care, life expectancy, and many other factors. Based on these, we can characterize species as either R or K selected. R-selected species have very high reproductive rates, but also very high mortality rates due to little parental care. If conditions are good and larval mortality is low, this type of species can increase rapidly. K-selected species have few offsprings, but live long and provide protracted parental care. While the total number of offspring produced in a lifetime is low, so is infant mortality rate. Regardless of the strategy, both are more than capable of meeting the needs of population maintenance. Table 6.1, Reproductive Strategies. Total population growth is based on several variables that include births, B, deaths, D, immigration, I, and emigration, E. The formula for total growth is B minus D plus I minus E, as opposed to natural growth, which is B minus D. Because deaths are included in the equation, it is important to understand the impacts of mortality on total growth. As life expectancy increases, mortality decreases. All things being equal, changes in life expectancy can cause population growth to increase. However, the effects can be offset by a decrease in births, which will eventually offset any population growth momentum. Different species have different maximum lifespans. If we consider these lifespans as well as reproductive strategies, we can generate graphs which represent survivorship over time. These survivorship curves are useful in comparing life strategies among species. Survivorship curves vary by species. There are three general patterns: full physiological lifespan if organism survives childhood, such as elephants and bears; probability of death unrelated to age, like gulls and mice; or mortality peaks early in life, for example, trees and fish. An illustration of survivorship curves. Based on analysis of mortality and reproductive strategy, we come up with three survivorship curves. There are type 1, type 2, and type 3. Type 1 species are characterized by low infant mortality and long lifespans. Most mortality occurs late in life. Type 2 species have moderate infant mortality and die randomly over time. This is common for many small mammals and birds. Type 3 survivorship is characterized by high infant mortality and only a few individuals living to a mature age. Most fish and many invertebrates exhibit this type of survivorship, type 3. So, why does all of this matter? If we wish to protect and conserve species, factors affecting growth must be included in any conservation plan. One question asked by many ecologists: what is the smallest population possible to still be able to maintain the population? This is important because small populations tend to have less genetic diversity, making them susceptible to changes in gene frequency. One outcome of small population is genetic drift. Genetic drift is a change in gene frequency due to a random event. For example, if a population suddenly undergoes a split or decrease in number from mortality through random chance, a gene allele, version of the same gene, that had previously been rare may now become common. This is drift. Other genetic issues can arise with a change in population size. A founder's effect and bottleneck occur when a population suddenly decreases in size. If the decrease is due to a subpopulation breaking away to start a new colony, it is a founder's effect. If it is due to a mass die-off, it is a bottleneck. The Amish are an example of a founder's effect, while cheetahs underwent a bottleneck approximately 5,000 years ago. An illustration of genetic drift.